Okay, now in the case of capacitors, we also looked at capacitors in series and parallel and the combination of the two and so on. But we also learned that sometimes it is not quite possible to simplify the circuit in series and parallel, eventually get equivalent capacitance. Okay, do we encounter the same complication here in the case of resistors? Okay, so let's take a look at the next example. What about this? Looks quite simple. I have points A and B. There are 5 resistors: R1, R2, R3, R4, and R5. Now, suppose you don't have R5 in the first place. Okay, this one is gone. Then, what is the equivalent resistance? How will you calculate the equivalent resistance between points A and B? That will be a simple job, because you realize that without this branch, you got path 1, path 2, unbroken in each of them. Okay, so R1 and R2 are in what? In series. Oh, they're not broken. The connection does not branch out. There's no such a path. And R3 and R4 also in series. Okay, and what will be the equivalent resistance? Well, simple. Add R1 and R2 up, and then add R3 and R4 up. This branch is in parallel with the next branch. That's it, right? But that is assuming that no R5 does not exist. What if R5 does exist? Okay, if R5 does exist, then you got a current flowing through R1. It's going to split up between this guy and that guy. So R1 and R2 are no longer in series because it splits up. They don't have the same current anymore. Okay, now R5 is not connected in series with R1, neither is R2. But what about the argument that R5 and R2 are connected in parallel? They start from the same point, right? But do they end at the same point? No, they don't. This R5 ends here and R2 ends there. They're not connected in parallel either. So you say, oh, don't worry, how about R5 and R4 connected in parallel with R2? No, that doesn't work either, because R3 comes in to break this path, so the current through this guy and through that guy will not be the same. Okay. As a matter of fact, this simple looking circuit is a case where you cannot simply break it down, simplify the circuit using just series or parallel connection. This is a more generalized circuit. Okay. So how do we deal with that type of circuit? There will be general rules which allow us to calculate the equivalent resistance of any circuit, including this guy. Okay? But before we introduce that, I want to look at a special case. I want to look at a special case first. This particular circuit, featuring a fifth resistor connecting this point and that point, one for the upper branch, one for the lower branch, can be named so-called Wheaton's bridge. Okay, and this fifth resistor is obviously the bridge. Now, even though in general it's not that easy to calculate the equivalent resistance between points A and B, you can imagine how greatly it can be simplified if R5 is removable. I can take away R5, then things will be simple. But of course, in general, you cannot do that, because when you put in R5, a current will start to flow, right? The current will start to flow from here to there. Unless, of course, the potential here and the potential there happen to be the same, right? If they have the same potential, then even if you remove R5, it's not going to affect the circuit at all, because R5 had no current to flow in the first place. Okay? Or suppose you didn't have R5 and you connect R5 in, nothing's going to happen, because these 2 points being at the same potential, no current will be flowing through R5 anyway, so it doesn't matter whether you have R5 or not. Okay, in that case, we say this bridge is balanced. Okay, balanced meaning these 2 points have the same potential. Now my question is, what does it take for these 2 points to have the same potential? Okay, what does it take? Turns out you can balance the bridge by making one of these 4 resistors adjustable here is a symbol for an adjustable resistor. You put a little arrow across one of these resistors, then we say this resistor is adjustable. You can change its resistance. Suppose I adjust R1 such that the bridge is balanced, meaning the current through R5 is 0. Now again, this happens because this point and that point have the same potential. Now if the current through here is I1 and the current through here, we call it I3. Okay, if the bridge is balanced, these 2 points must have the same potential. So if you look at these 2 resistors, you'll find that the potential difference across them must be the same, right? Because they start from the same point A, same potential VA. One goes to here, one goes to there, but these 2 points have the same potential. So isn't it true that the voltage difference across this guy and that guy will be the same? Okay, but what is the voltage difference across the first one? Wouldn't that be I1 times what? Times R1, right? For that guy, wouldn't it be I3 times R3? And they're the same. Right? They're the same because these 2 points have the same potential in a balanced case. Now, let's look at the current going through here and the current going through there. Since no current flows through R5, I1 must equal to the current flowing through here, which I call I2. Right? And I3 must equal to the current flowing through that one, which I call I4. So I1 equals I2, I3 equals I4. Now let's consider Ohm's law applied to R2 and R4. This resistor starts from this potential, ends up at VB. That one starts from that potential, ends up VB. But these 2 potentials are the same, so once again, the potential difference across R2 equals that across R4. Okay? So we say that I2 R2 must equal to what? I4 R4. Okay. And don't forget, I1 and I2 are really the same. I3 and I4 are really the same. We can actually get rid of all the currents, I1, I2, I3, I4, by dividing one equation with the other. Because then we get I1 over I2, which is 1 because they're equal, and I3 over I4, which is also 1 because they are equal. So let's divide this equation by that. Okay. You got R1 over R2, and then I1 over I2, which is just 1, equals what? R3 over R4, because I3 cancels with I4. So this is the condition for no current to flow through R5. Okay, in order to balance the Wisdom bridge, it requires this equality. I can write this as, you take the cross product, R1 R4 equals R3 R2. This is the condition for the bridge to be balanced. Okay, then the problem is quite simple. There is no current flowing through the bridge. It is balanced. Can you think of some application of this Wisdom's bridge? Well, one thing you can think of is, suppose out of these 4 resistors, one of them is unknown. Let's say R4 is unknown. I don't know what it is. Okay. In general, if you just put an arbitrary value of R1, you're not going to balance the bridge, right? You're not going to balance the bridge. So if you put an ammeter here, you are going to measure a current. Okay? It's not 0. But what you can do then is you can fine-tune R1 because it's adjustable, right? You fine-tune R1 such that at some value of R1 you find there is no current flowing through it. The bridge is balanced. That equation must apply. You know R1, you know R2 and R3. You can solve for that unknown resistor, R4. So this is a way to measure an unknown resistance. Okay, that was just a special case when the bridge was balanced. If it's not balanced, we have a more complicated circuit. So let us look at a set of general rules, okay, general rules that will allow us to deal with any electrical circuit without having to necessarily break them down into series and parallel connections. It turns out there are 2 rules to deal with that. These are called Kirchhoff's rules. Okay, 2 rules. These are called the rule of the nodes, or rule of the junctions, and the rule of the loops. These are the 2 rules. They are based on very fundamental laws of physics, and they are very important they're pivotal in our understanding of how to calculate the currents or electrical resistance of any complicated circuit. The first one, the rule of nodes, otherwise known as junctions. Okay, suppose I have a point in any point in the circuit where current flows in and out. Like in this particular case, I look at point A, you got 2 currents flowing in, 3 currents flowing out. Okay, we call this point a node or a junction. Okay, what is the rule of the nodes? What does it say? Well, it says that if you add all the currents flowing into this node, it must equal to the sum of all the currents flowing out of the same node or the same junction. So in this case, I have I1 plus I2. These are the current flowing in. It must equal to I3 plus I4 plus I5. Okay? You can generalize to more complicated cases when you get many more branches flowing in, many more branches flowing out. What is the physics behind the rule of the nodes? Well, very simple. It's conservation of charge. Okay? Conservation of charge. You know charges cannot be created or destroyed. Everything must be accounted for. So let's look at a given amount of time, dt. During that time, a certain amount of charge entered this node, and that is I1 dt plus I2 dt, right? Meanwhile, a certain amount of charge must leave. That is I3 dt plus I4 dt plus I5 dt. Now, why do we say that the sum of the incoming currents must equal the sum of outgoing currents? Because this is just a point. A point cannot store any charge. Okay? So whatever amount of charge flowing in, the same amount of charge must flow out over the same amount of time in order to give space. Okay? And charges cannot be created on its own or destroyed mysteriously. So, you got charges flowing in. The only way to get rid of it for the same amount of charge to flow out. So therefore, incoming currents must equal to outgoing currents. Alright, this is the so-called rule of nodes. It's rooted in the conservation of charge. And when you look at a complicated circuit, sometimes you don't even really know whether a certain current is flowing in or out. You don't know for sure. It depends on how strong the battery is on this side and that side, that sort of thing. But you don't have to know in the beginning of the problem. What you can do is you can make an assumption. Okay, you can make an assumption that the current, for example, I3 flows out. Now, you can do a calculation. At the end of the day, if you find that I3 turns out to be positive, what does that tell you? It tells you your assumption was actually correct. Okay, you made the right assumption. The current actually does flow out. But if it turns out I3 was negative, what does that mean? It means you made the wrong assumption. The current in this branch is not flowing out, rather it's actually flowing in. Okay? So as long as you're self-consistent, that's the key here. As long as you're self-consistent, you will be able to find the direction of all the currents in all branches. And what exactly do we mean by self-consistent? Well, when we look at examples, we'll see how that goes. Okay, the second rule, the second of Kirchhoff rules, is the so-called rule of the loops. Okay, and what is the root of this rule? Okay, it is the conservation of energy. So it's also a very fundamental rule. So both of these rules apply in the most general case because they're rooted in the most fundamental law of physics. What is the rule of loops? Well, using gravity as an analogy again, suppose you start from let's say you start from the ground floor. Okay, you go upstairs, you go downstairs, you go upstairs and downstairs, however many times you go. As long as you eventually return to the same ground level, let me ask you, what is the change in the gravitational potential energy? Zero, right? And in particular, what is the change in your elevation? Well, that'll be zero. Now, elevation is proportional to gravitational potential energy. In the electrical case, it is analogous to electrical potential, which is also proportional to electrical potential energy if you put a charge in there. the rule of the loops traces the change in electrical potential as you move from one point to the next point to the next point in any self-enclosed path or self-enclosed loop in a circuit. So we start from this point, we go around and around and around. As long as you eventually go back to yourself, to the same point, shouldn't the change in potential be zero? In other words, shouldn't you return to the same potential value that you started with? Okay, but along the way, the potential can fall, can rise, depending on which element you go through. And but the total change in potential must be zero. That'll give you an equation. Okay, it must be a self-enclosed loop. It can branch out, it doesn't matter as long as you follow an imaginary loop which comes back to itself. Okay, this does not have to be a single wire. Again, you can have branching out. Just don't care about that. Just follow. Just stick with this single loop. As long as it comes back, you will get the same potential back. So the net change in potential would have to be zero. Okay, example. Suppose I start from point A in a loop. Okay, so we go through a battery, and we go through a resistor. We go through another battery, another resistor, another resistor, and then we come back. What can we say when we apply when we apply the loop rule to this branch, to this loop? Well, if this is epsilon 1, R1, epsilon 2, R2, epsilon, and then here is R3. Okay, what can we say about it? Well, we can say, starting from point A, imagine our loop flows clockwise, so you have to go through epsilon 1 first. As you go through epsilon 1, what happens to the potential? Does it rise or does it fall? We go from negative to positive terminal, so that is a lift in the potentials, right? If the potential goes up by epsilon 1. And then you have to go through R1. Suppose the current flows this way, assuming the current flows this way. So you follow the direction of the current through a resistor. What happens to the potential? It has to go downwards, right? Not upwards, right? So it's minus I times R1. Okay, that will let you arrive at this point, at which point you go through another resistor, another EMF, that is, in the same direction. Actually, let's make it more interesting. Let's say it flows in the opposite direction like that. Okay, it is oriented in the opposite direction. So this time you're moving from a positive to the negative terminal of a battery. What happens to the potential? Has to go downwards, right? By how much? By epsilon 2. Then you're here. Once you're here, you have to go through both of these. Okay, so minus I R2 minus I R3. This, then you will land here, and there's nothing going on here. It's the same wire, and then what's that equal to? That will be equal to 0, because this is the net change in potential starting from point A, ending at point A, so it should be 0. That will be an example of the rule of the loops. And you can branch out if you want to. You can put something else here. The only difference is that if this current is I, that current is not I anymore. So you have to use a different I. Let's call it I prime and I prime. It doesn't matter. You don't have to include everything in the same loop. You can just say, I'm going to follow this. I'm going to ignore that. Okay, as long as you recognize that the current here and there are not the same. You can do the same. You can still follow just one loop, or you can take that loop if you want to. Any self-enclosed loop will do. So that is the rule of the loops. Now, with the rule of the nodes and the rule of the loops, we will generate enough equations to tackle the circuit diagram of any complicated circuits. Okay, any complicated circuits. In particular, if you draw me a circuit diagram with all the resistors and all the EMFs in place, I can tell you how to find the current in every single branch. Basically, I can solve the circuit for you. Okay. In particular, let's go back now to the unbalanced Wheaton bridge in the problem that we left out. We just looked at the special case, right? This is the unbalanced Wheaton bridge. That was the balanced case, but now unbalanced. This equation is no longer valid. Okay, there will be a current. We don't even know the direction of the current, whether it flows from top to bottom or bottom to top. But don't worry, we're going to use the general idea of the Kirchhoff's rules. and we can always calculate. We can always find the current in every single branch, and from that we can always find the equivalent resistance from point A to point B. And at this point we're running out of time, so we're going to start this problem in the beginning of the second part of this lecture.